All right, this is a problem involving constrained objects, 10 kilogram mass hanging down here, 5 kilogram mass going to slide up with some friction between it and the ramp. We're supposed to calculate the tension in the string and the acceleration of the masses. So this is kind of a long problem, so kind of be patient and pause when you need to, and if you have to fast forward, you can do that as well. The free body diagrams are always the first best place to start, and let's do the one on the 10 kilogram mass first. Basically, this hanging object, we're just going to have a tension upwards from this cable, and we're going to have the force of gravity on the 10 kilogram mass downward as such. So there's our FBD labeled. And now with this crate which is on the ramp, we want to employ using a tilted coordinate system. So we take our usual XY coordinate system and we tilt it so that the X lies along the plane of the ramp, the horizontal, and then we have a Y direction which is perpendicular to the ramp, and that's the easiest way to resolve the force components, okay, along the direction of the motion. So speaking of the direction of the motion, we also need a frame of reference or a coordinate system. It's easiest, it is easiest if we kind of let the direction of the motion be the direction of the positive acceleration, and that'll be the positive direction for our forces as well. So we would choose that up the ramp for the 5 kilogram crate, and for the falling crate, this is a little different now. We're going to choose the downward direction to be positive as well. That way, all of our vector components, if we have a positive acceleration coordinate system and a positive acceleration coordinate system in the direction of the motion, that allows things to be a little more simplified when we have to substitute in for some things later. The free body diagram on the crate is going to look something like this. Then we're going to have, obviously, the tension of the cable here, which would be pulling upwards on the crate, T. The force of friction between the surfaces is going to be down the coordinate system here, so we'll call that the force of kinetic friction. It would be down the ramp. The normal force will be away from the ramp itself because surfaces always push perpendicular to themselves, and gravity is going to be straight down towards the center of the earth. Okay. Now it's this gravity vector we have to work with in our tilted coordinate system a little bit, all right, because we want to resolve the components of gravity along the ramp. One's going to be downward like this, and the other one would be downward like this, and this angle, theta, is the same angle here, theta, as the angle of the ramp. And the reason for that, again, is this coordinate system has been tilted away by this angle 40 degrees, and that leaves this angle, I'll show that right here, that leaves this angle, whoa, that leaves this angle in here to be the angle theta. Okay? All right, so this side is the adjacent side. So this side is going to be FG cosine theta, and is pointing in the negative downward y direction. This one's pointing in the negative x direction, so this one is negative FG sine of theta. Sorry, that got a little cramped in there. All right, so there's our vector triangle. After we've got our components, the next thing to do is to fill out our T-chart. So notice for the 10 kilogram mass, that's pretty easy. If we're choosing the positive acceleration to be downward, we'd have minus T, which would be up, and plus Fg, which would be down. The T-chart for the crate, we've got the tension up the ramp, we've got a component of gravity down the ramp, a component of friction down the ramp. Okay, those two have no components in the y direction. Force of gravity does have a component which presses it into the ramp a bit, this Fg cosine theta, negative because it's into the ramp. And we do have a normal force from the ramp pointing up and away. So in this case, we have our T-charts, and pretty much from here on out, it becomes a lot of algebra. And I'm going to leave things in symbols because that's usually the best way to do things, although I know it looks tedious as we go along. So we would want to write our x and y equations from our T-charts to begin with. So in the x direction, you sum these all up, make it look like an equation, and we know it's accelerating up the ramp in that x direction. Of course, there's no acceleration perpendicular to the ramp, so AY is 0, so we can set these two forces equal to 0. It's in the equilibrium in the y direction, right? And then our equations from for our 10 kilogram block are 0 in the x direction, of course, and in the y direction we'd have Fg minus T equals the MA for the 10 kilogram mass. All right, we've got all of our equations in motion, and there's 1, 2, 3 that we can use that we're interested in. Now we want to take it the next step further in terms of the algebra. So if you take a look, what we have to do here is use our familiar equations for gravity, mass times g, for friction, mu times the normal force, and we're going to put those values into each equation. So first of all, if we solve for this y equation and find out the normal force is the portion of gravity which is pushing into the ramp, we could set Fg equal to m5 times g. That means the mass of the 5 kilogram. And if we do the same thing for the x direction, right, this Fg is our m5g here, and our force of friction is going to be mu times our normal force. So I'm just restating this x equation with these terms plugged in. We can do that same thing here with our y equation from the 10 kilogram mass. We'll just put m10 times g in for this force of gravity minus the tension equals mass of the 10 kilogram times acceleration. Alright, so we've just restated those three equations in terms of some more fundamental constants that we usually have in the problem, or not constants, but values that we have in the problem. Now comes the step of rewriting things and combining terms. So once I've got this x equation all written out, alright, I just transferred it down to here. What we're going to do from there is substitute in this m5g cosine theta for the normal force right here, and that's taken care of right in this step. So now we've got everything broken down about as far as we can in this equation, all right, in terms of its fundamental values that we could be given or that were known. And now, whew, that's a lot of work, right? Okay, it looks like a big complicated mess, and it kind of is. But what we see, we're going to have to, if we're going to solve for the tensions and the accelerations, the things that we don't know, we have our systems now don't know the accelerations here and here, don't know the tensions here and here. So what we have to do is substitute in for t, get rid of one of those unknown variables. So the easiest way is to take the t here, express it in terms of the 10 kilogram mass and these quantities from this equation, and substitute it in for this t right here. That's what we're going to do next. With this green arrow, we're going right into this t right here. Alright, so bringing those over, I'll leave those in green. We can see that we substitute in for our t, and now it's a big algebra puzzle. What I'm going to do is I'm going to move this m10 times a over to the other side. Okay, you'll see why. And then what I can do, once I've done that, alright, is I can pull out this acceleration and this acceleration are the same, right? So we pull the a out, and we can re-express this and divide. Okay, so let me show you the division part here. We're going to divide both sides by m10 plus m5. So we lose it from this side. We're also dividing it on this side, and then we get for our final expression for the acceleration this big value right here. Okay, if we were asked to do things in terms of only symbols, we would be done. Alright, but they asked us to get some numerical values. So now is the part where we can finally go and plug some numbers in. And like I say, I wanted to show you working a problem all the way through with symbols. Some of you might find it, as you're first starting out, more convenient. It's not the best practice, but more convenient to put some numbers in earlier. If you crank it all out and calculate it, you'll get an acceleration of 4.06 meters per second squared up the ramp. And then what we do is we come back up to our other equation that we had way up here. And I'm just bringing that one down and substituting in our value that we had for the acceleration here now. And we can find out that the tension in the string was 57.9 newtons. Alright, that's a long problem, but you can see, again, to recap the process, it's getting your free body diagrams right and your coordinate system and your angles right. making sure that your signs are lining up for a chosen positive acceleration and positive acceleration coordinate system in the direction of the motions, writing your systems of equations out, and then just being very careful with your algebra not to make a mistake. And eventually you'll get there, okay? And good luck.